All right, welcome to Digital Audio Signal Processing. This is Unit 1, where we cover fairly generic DSP stuff, and this is Note Set 4. We're going to talk about measuring the impulse response and/or the frequency response, mostly of a room we're going to be talking about because we'll be using that later on. But we'll also need to know how to measure the impulse response or frequency response of some existing audio system, maybe an analog audio device or system or box that we want to mimic with digital signal processing. So it would be handy to be able to measure the impulse response and/or the frequency response of that. Or maybe we've designed something and we want to test it in the lab to see if it does have the frequency response that we intended. So that's the idea. Got a couple readings here. Both of these are pretty accessible readings. And this one in particular by Farina, he's really the guy who kind of, is the main driver of a lot of this stuff. He came up, that paper was something where he came up with a whole new idea using a so-called swept sine signal, and is kind of the ultimate way of doing this. So we'll get to that at the end. So we are doing audio work in this course. So we're trying to characterize our audio devices, or maybe characterize the room acoustics that they're going to be used in, or characterize the room acoustics so that we can simulate it. We can make a simulated reverb, something like that. So that's kind of where we're heading. And so this is going to allow us to measure the impulse response or the frequency response. So impulse response and frequency response really only makes sense to talk about, at least in the form you're familiar with, if the system is linear. So if you have a linear time invariant system, you can characterize it with its impulse response or equivalently with its frequency response. Now, a lot of times there are some nonlinearities involved, and those could be either unintentional or intentional. So in an audiophile amplifier, if there's any nonlinearity in there, it wasn't by plan. The goal is to make those as linear as possible. But if you're a guitar player, you know that guitars that distort, or guitar amps that distort, are desirable. And so people purposely build them to have nonlinearities that can be exploited. Same thing with guitar effects boxes like overdrives and distortions and fuzz boxes and things like that. So to characterize something like that, you need more than just the impulse response or the frequency response. So we'll talk about that throughout the course, but right now we're just trying to focus on how to measure the impulse response and frequency response of a linear system, but there might be some nonlinearities involved. So if we're using a speaker and a microphone to a speaker to send a signal into the room, and then a microphone to pick the signal up, if we're trying to measure the impulse response of the room, those things could have some nonlinearities in them, and that could cause us problems. So we'll see how to get around that as well. So let's start with the simplest idea. You've got a room. You want to measure its impulse response. So you walk into the room and you create a delta function, which then goes into the room, and you stick up a microphone somewhere and it measures the impulse response of that room. And then you digitize it and you put the samples into your computer. Now, this is simplified a little bit. I don't show the microphone and an amplifier and so forth, but the principle is very simple. But the question is, how do we actually do this? Here's a picture that illustrates how we might do that. Something that makes a delta function. And then we've talked about how Well, I guess we haven't talked about that yet. There's various reflections throughout the room, and they all end up being picked up at some microphone. And I'm showing here a binaural dummy head, and I'm just giving some references to where I've taken these pictures from. No real need to go to those places, although there are some interesting stuff there. But binaural dummy head is often used when measuring these things. You put the head in the room. It's just a dummy head, often made of material to mimic the acoustic properties of skin. You put a microphone in each ear position, and you can record a stereophonic version of the impulse response. But that's not the focus of what we're talking about here, but just wanted to point that out. And then we record it, and we have the impulse response. So it looks simple in principle. The question is, how do we make that delta function? Remember, this is continuous time. So a true continuous time delta function, well, that's infinitesimally narrow and infinitely tall. So hard to actually create. So people have tried different things. And I'm just showing references to places that I've borrowed graphics from. This looks to me like Teddy Roosevelt. Maybe, I don't know why he's measuring the impulse response of a room. But anyway, use a starter pistol with blanks, right? You shoot that off. That makes a very narrow, very loud sound. So that might work. You could take a balloon, fill it up, and then pop it with a pin. Also makes a very loud and narrow kind of impulse. A hand clap. You could just walk into the room and clap your hands. So I often do that when I go into a room and I want to kind of get a sense of what are the acoustics like in this room. You just clap your hands and you hear the echoes. So you could do that. And somebody actually wrote a scientific paper on building this clapboard out of pieces of wood, and then they tested it. I think that paper might be available for free, but I'm not sure at that link. But you can track it down if you want. But it's, the things we'll see show you how to do it without using a wooden clapboard. But the question for all of these and anything else like this that's directly making the acoustical sound, are they actually even usable? Well, they're all usable to some degree. People have used them, but they all have problems. So do they really make a delta function? Or said another way, if you were to just measure the spectrum of that signal, is it flat? And is the sound going out in all directions? And can we make it loud enough? So starter pistol, yeah. Clapboard, maybe. Hand clap, I don't know. You've got sounds in the room from the HVAC system. So you got to get loud enough to compete with that. And then a big part is it repeatable? So if you clap that clapboard together once and then measure, and then you go to another room and you do it, are you creating the same stimulus signal? It turns out that none of these things are good, okay, for any of this. So they are a rudimentary way. Plus, they're good for measuring the impulse response of a room, but what if you want to measure the impulse and frequency response of some device? Well, then you're going to need a microphone to measure this as a generating signal or a stimulus signal. So not necessarily the most flexible way to do this. So we could use speakers. And these are things that Farina created, two different versions of this kind of near spherical stimulus speaker. So I don't want to go into the details of that. You can go grab that PDF of his presentation. But basically, he's putting lots of little speakers on, I think this is a dodecahedron or something like that. And then he's going to lots of trouble to make sure that this thing works well. Very linear Class D amplifiers and ways of connecting it to a computer and special little speakers that have long excursions so they don't go into nonlinearity, and wrap these speakers all around. So we're just seeing them on one here, but every one of these faces has the same setup. And that makes it omnidirectional to a large degree, very, very omnidirectional. And since you're just putting a signal in that's coming from a computer, it's very repeatable. So that's very, very nice. But can we make a delta function from this? We've been focused on making a delta function. And so the question then becomes, well, do we need to, and should we make a delta? So there are some issues there. So here's the challenge of making an electronic signal that looks like a delta function. And this is true for the room scenario, going through a speaker setup like Farina just showed, or just shoving this into, a piece of audio equipment to measure the frequency response of that. The bottom line is we can't really make a real delta because real deltas aren't even real functions. So even mathematically, we have some issues with delta functions. But physically, it's got a width of 0 and a height of infinity. When's the last time you saw a voltage with a voltage of infinity? Well, if you have seen one of those, you probably aren't here any longer to report about it. So maybe we just make it very narrow as we can and as large as we can. We might be able to make some electronics, probably very expensive, very heavy, that could make those things, make something very narrow width and very large amplitude. But that narrow width, as soon as we shove it into those speakers, they've got inertia. So the speakers are going to limit, because of their inertia, they'll spread out any narrow electronic signal. So that's a problem. And then very large amplitude, again, could do it with electronics, but you're asking the speaker then to make a huge excursion because of the large amplitude, and it's not going to do that. It might damage the speaker, and the farther you ask a speaker to go along its excursion, the more nonlinear it's going to be. And also, just forget about doing it for a room. Are you going to put a 500 volts little pulse into your beloved audio amplifier? I don't think so. So maybe we don't need a delta. If we're clever, we can use some other signal and then use our cleverness in developing some DSP processing that we do afterwards. So what kind of signal? We want to make sure that it's, loud enough so that we can compete in a room setting against the HVAC system and things like that. But we don't want to damage the speaker that we use to create this probing signal. So we want that energy spread out uniformly over time. So that's the idea. But what signal? What should we use? So let's set this up and analyze it. That's what we do as DSP engineers. So we've got some discrete time signal. We're trying to figure out what we should make that be, but we're going to create it with our computer, and we're going to run it through a digital to analog converter to create some existing, or some real world continuous time signal. Now there'd probably be an amplifier there and there'd be a speaker there. I'm not showing that, so that's kind of all built into this DAC. So that box is really a DAC and an amplifier and that crazy speaker that I showed you from Farina's work. And it creates this signal that in this setting we're talking about spewing that out into a room. But if we got rid of the Farina speaker and just went from the DAC into an amplifier to boost it up and then took that into whatever device or system we wanted to measure the impulse response of, we could do that. So it could be room or it could be some device. But whatever it is, it's got an impulse response of h of t. And so these two things get convolved. And out comes some signal y of t, continuous time signal. In the room setting, that would get picked up by a microphone and an amplifier and then into an A to D converter. And in the audio device or audio system setting, this would just come out and could probably go right into an A to D converter, maybe a little bit of an amplifier there to just provide a little boost. And then we get a discrete time version of that. And here comes the clever DSP. It's not going to be clear right now why we do this, but the proposal is to take that output and convolve it with the time reversed stimulus signal. So both of these can come from our computer. All of this is inside our computer. So we can make those be anything we want, really. And our task here is to figure out what would be the right choice and to see why this time reversal idea is good. And then we'll move on from there to look at a more generalized version. So I'm going to ignore some of the real world issues, like, I'm not going to worry about the effect of the DAC or the A to D converter or any of the amplifiers and speakers there and microphone and speakers here. And I'm not going to worry about any nonlinearities that might be involved. So theoretically, perfectly, we know that y of n is going to be the x of n convolved with a discrete time version of h of t. So we could analyze this much more in much more detail, but this is the basic idea. This will give us a good feeling for how this is going to work. So we're thinking all in terms of discrete time, even though there is this embedded continuous time thing in there. By putting a DAC here and an A to D converter here, we've effectively converted it into an equivalent discrete time system. So DTFT properties says convolution in the time domain corresponds to multiplication in the frequency domain. So those are the DTFTs. DTFT of the signal and the DTFT of the impulse response, that's its frequency response. So here I'm using this kind of notation. In an earlier note set, I used frequency response where it was h of e to the j omega, but this is a more typical or common way to do it. Now, what is happening to y? Well, y then gets convolved with the time reversal. So this whole thing gets convolved with the time reverse version of x, but then just using some common properties of convolution, I can realign all that. And I've put parentheses around this so to evoke the idea that, oh, let's look at that, because that is the thing that ends up being convolved with h of n. Well, let's look at it over in the frequency domain. So if we take the DTFT of that, we again see three signals being convolved. So that would be three things multiplied over in the DTFT world. So one is x of n, so there's its x of omega. Then we have x of minus n. So time reversal property tells us, I used to have, I guess I lost one of my little call outs here. This comes from the time reversal property of the DTFT. So you can go look that up. And then DTFT of the impulse response is the frequency response. And then we have something times its conjugate is magnitude squared. Okay, nice. So that's what we have. And now let's just name some things here. We're going to say that this convolution of x with its time reverse thing, we're going to call that the autocorrelation of x of n. There's a reason for that. I don't want to go into it right now, but maybe you've run across that kind of thing in some other DSP studies. But look, if that thing is a delta function, and I just put a c out in front just to allow it to be some number times the delta function. Remember, this delta function doesn't go to infinity. It's just a string of zeros, then a 1, and then a string of zeros. Fundamental difference between continuous time delta function and discrete time delta function. And remember, we've kind of transformed this into an equivalent discrete time system. So that's why we're able to think this way. So if this ends up being a delta function convolved with h of n, well, a delta function convolved with anything gives back that thing. Well, there's the c out in front. So that means the thing coming out of here will be at least proportional to the impulse response of this effective system. That's only if this is true. So that tells us how to pick. We need to pick some signal such that when we convolve it with its time reversed version, we get a delta function. Interesting. And we can also see this in the time domain, or I'm sorry, in the frequency domain. So remember, this turned into this, and so this will turn into just a constant. So in other words, we're saying that the signals that satisfy this are exactly those signals that have a flat constant DTFT or a flat spectrum. So we say that that signal is in some sense white, and what we're doing is borrowing terms from random signals, white noise, which borrowed that term from physics, white light. So that's the idea. And so we can see that if this becomes C, then the DTFT of the output signal is the frequency response, at least proportional to that. So that's the idea. So if we can make such a signal, then we can find the impulse response, or equivalently the frequency response. Nice. Now, let's look at this condition here to see what we need to be able to do this. And the literature refers to this as deconvolving. And there's a reason for that, right? X gets convolved with H, and then we deconvolve it to extract the H from that resulting signal. Okay. So we've already seen that if we use a signal such that its autocorrelation is a delta, then we can extract the impulse response, and then we could convert that into a frequency response if we want. So here's a picture of how this looks. We start with some stimulus signal that we make, and we're kind of envisioning this in the time domain, but really this would start in discrete time, and we would do this in the discrete time. We literally just flip it in place, and so now we get a time reversed version of that. And then what we're evoking here is this is the device under test, whether it's a room or an audio box or an effects box or an amplifier or whatever it is that we're testing. And the idea is we put the stimulus into the device under test, then we convolve its output with the time reversed, and the thing that we get is the impulse response. So there's a little bit more involved here, but that's the basic idea. So I'm just using this symbol here to represent that autocorrelation of X. That's just a common symbol that's used. Or in other words, we need a signal whose spectrum is flat. And so, as I said, it's a white spectrum in some sense. And I alluded to there being a random signal concept of white noise. And we're not really talking about that, but it is related. So basically, we're looking for a signal that has that characteristic. Now let's generalize this. It's always good to say, well, I've constrained myself. Let me back up a slide or two here. Yeah, just right here. I've constrained myself. I said that I'm going to put this signal in, and I committed to using time reversed version. maybe I don't have to do that. Maybe there's a more general way to do that. So let's analyze this way. I put in some signal x of n, and now I'm going to convolve with something else. And the question is, how do I find out how that's related to the x of n? And then a natural question is, does that provide me with any advantages? Does it allow me to choose a different x of n than I would in the more specific scenario? And would there be some advantages to that? And so in the literature, they talk about this f of n being the inverse filter of the signal x of n. So we say we convolve with the inverse filter. And so in the previous scenario, we said, well, we choose x of n to be some flat, a signal that has a flat DTFT, then its inverse filter is just the time reversed version. Well, maybe we don't pick this to be something that has a flat spectrum. Then maybe this is not the time reversed. And maybe by generalizing that, we develop a little bit more flexibility that might be useful to us. So let's look at this. Well, the first thing we need to know, this is pretty clear, is whatever x of n is, doesn't necessarily have to be flat, but it can't be 0 at some frequencies. Okay, it has to be non-zero over all frequencies. Because if it's 0 at some frequency, then we're not probing the system at that frequency, right? Because as this signal goes through, the output here, its DTFT is equal to x of omega times h of omega. And so if there is some frequency where this is 0, then this will also be 0 at that frequency. And the question is, then what was the value of this at that frequency? Unknown. We don't know. So we need this condition so that we can probe all frequencies. So that's really the only condition we have. And there are, practical things that we might bring to bear on this, but from a theoretical point of view, that's it. You can pick this to be whatever you want as long as this condition is satisfied. And then how do we find the f of n? Well, there's going to be some signal that when convolved with that x of n gives us the delta function, just like we saw with the time reversal version of that. So let's look at this in the DTFT view. So this converts to that product, and this converts to just the constant. And so now we can easily see, right? Swing this over to down here. Aha, there's why we needed that. So it's nice when you can come up with a physical rationale for something, but then it falls out of the mathematics as well. Okay, so pick your x of n, make sure that's true, divide that x of omega into some constant, doesn't really matter what it is, and that gives you your f of omega, and now transform it back, and that tells you what your f of n is. So with some analysis and or numerical computation, you could figure that out for just about any x of n that satisfies that. And so now we have something that looks like this. And again, this is just kind of, iconical view of this. We have our stimulus, and the author of this is kind of giving away what we're going to end up using for our stimulus signal. I won't say, but you can kind of see it there. And if you come back here after we've gone through some of the subsequent slides, you'll go, yeah, I see it too. And so at least in principle, we're going to use the FFT to compute some sort of spectrum here, and then here's the inversion. And those pictures don't quite work out. I think what the author is doing is really showing this in dB, and then dB inverting is just flipping on the dB scale. So that's kind of what they've done. But mathematically, that is literally what we do. So you could do that. And then you compute an inverse FFT and you get your signal. It's going to end up perhaps looking something like that. And you you run this into the device under test, convolve it with your deconvolution filter, and the thing that comes out will be your impulse response. Now, there are some practical issues to come up with here when using the FFT, and technically you're using the DFT. The FFT is just a fast algorithm to compute it. You're going to have to pay attention to zero padding and all sorts of other things, windows and so forth. So there are some practical gotchas there, but this is the basic idea. Okay, so how do we choose this signal now? Are there some that are better than others? So we have this new view here, and let's go through and look at this. So like I said, we can choose any signal that we want as long as it probes all the frequencies. It turns out that if we pick this so that this is a constant in magnitude, then this is just x of minus n if the probing signal is white, or the stimulus signal. But are there other factors that we should consider? That's a good question. So we should think about how easy is it to make this x of n and make the f of n. I just alluded to some difficulties doing those FFTs and inverse FFTs. Be nice if we could avoid doing all that. If we could just analytically say, here's a good x of n and here's what the f of n is, and we just program that in. So that would make it very easy to make these things. There are some issues. I'm not going to go into the details, but there's issues with this conversion from x of n to x of t, and then vice versa from y of t to y of n, but it's more critical here. If you address it at the input side, the output side pretty much takes care of itself. But we want to make sure that if we're creating a signal x of n here, that satisfies all our discrete time conditions, because remember, we viewed this as a discrete time system with an impulse response h of n. We need this thing to inherit the properties of x of n. And it turns out, without going into the details, it turns out that doesn't always happen. So we need to worry about that to some degree. And then there's measurement noise. So right here, we're going to, for a room, we're going to put a microphone there, and there could be some noise in the room from the HVAC system or whatever. And so we want to make sure that our system isn't totally made completely useless if there is some small amount of noise. So maybe the choice of X would be governed or driven somewhat by that. So that's an issue. And is it robust to some nonlinearities that are in the actual measurement system? Well, there's nonlinearities in the DAC and nonlinearities in the A to D converter. And there's going to be nonlinearities in the speaker that's here and maybe the amplifier that's driving the room. There's going to be a microphone here. There could be nonlinearities in that. The room itself, if we're measuring the impulse response of the room is going to be linear. That's pretty straightforward to kind of convince yourself of that. But if we're putting this into an amplifier or some audio device or something like that, there's no guarantee that the device you're measuring is linear. So we want to have some ability to deal with that. So that might have some impact on this as well. So armed with all of that, I'm going to take you through a little bit of history of using this, different types of signals for measuring RIRs, room impulse responses. But this could also be used, at least for some of these, for measuring the impulse responses of other devices that aren't rooms. So we've already talked about making some sort of approximate impulse response, right? Clap your hands, shoot a pistol. None of those are very good. We talked about the limitations of making an electronic impulse and so forth. So this has very much long ago fallen out of favor, although for some rough and rudimentary measurements still might be useful for a room. The next thing people looked at was driven by the first method that we talked about, putting in a signal with some sort of white spectrum and then doing that time reversal. So these were called MLS, or maximum length sequences. There's some they're fairly general. They're not just for audio, and you can find a lot of literature on them from back in the 70s and 80s. And basically, it was in audio, it was pseudo-random binary signals. So they just fluctuated between +1 and -1. They were very easy to make back then inside the limited computers of that day. But they had a lot of drawbacks. So they had problems with nonlinearities, and they had problems with that boundary going from x of n to x of t. And that took some doing. You had to periodize the signal. And anyway, nobody really uses those anymore. So enough said. Nowadays, it's pretty easy to generate more generic pseudo-random noise signals. So for quite a while, that was a pretty good driving signal. In fact, I remember seeing in the 90s and the maybe 2000s, you could buy stereo systems that came with the ability to measure the frequency response of your room and then correct for that. And when you played that, or when you did that characterization of your room, it would sound like it was sending out white noise, just a very loud hiss. So that was kind of driven by this. And then that would use the time reversed version to do that. But they also had some limitations. Not so much with the boundary between x of n and x of t, but nonlinearities. If there were any nonlinearities involved, whether it was the thing that you were trying to measure or the system you were using to measure, which was more often the case when these things were being used, they had some serious problems. So again, not used anymore. One way you could do this, and this isn't something that was really ever used except for perhaps in the laboratory. You could just take a sinusoid and run a single sinusoid through the system and measure the amplitude and phase of the output sinusoid. And then do it again for another sinusoid. In fact, you could mechanize this, so run a sinusoid for several seconds and then measure it. But it was still pretty slow because you every time you switched to a new sinusoid, you had to kind of wait for the system to settle down to so-called steady state. And it turns out when you're doing this kind of thing, without going into the details, you can actually measure the nonlinear parts of the system. So that's very good. And really the only issue with that is that it's slow and kind of cumbersome to get. But let's think about that. If we're stepping through sinusoids, let's take that to the limit, right? Let's make the sinusoid be at a single frequency for an infinitesimally long period of time. Now we want to hit every frequency, right? Well, here we were kind of just on a fine enough grid, but what if we swept the sinusoid's frequency through all possible frequencies, just hitting each frequency just for an instant? That'd be interesting. And that is actually what is done. And so this is the premier way of doing this today. And that was what Farina, some people came before him and did a so-called linear sweep of the sinusoid's frequency. But Farina discovered that an exponential sweep is even better. So you get excellent performance. Nonlinearities have little impact, and in fact, you can actually measure the nonlinear responses if you use the exponential version of this. You get a pretty fast answer, and it's really good. So we're going to spend the rest of this set of notes looking at how we do this swept sinusoid thing. So let's look at linear sweeps. So they were around for a while before Farina discovered that exponential sweeps were even better. So let's look at linear first, then we'll generalize it to exponential. So what does it mean for a sinusoid to have a linearly changing frequency? Well, what does it mean for your car to have a linearly changing speed? Same question, really. Speed is a derivative of position, and frequency, what's its units? Radians per second. Oh, that's a rate, right? The rate of change of phase relative to time. So let's look at a regular sine wave, right? Kind we see all the time. This has a frequency of omega 0. Well, let's extract the phase, right? This is the angle of the sinusoid. So it's not just the phase shift, it's the whole time varying phase of that sinusoid. So it's linearly changing. It's changing as a line, right? Slope of omega 0, intercept of theta. So if we took the derivative of that, what do we get? Omega 0. So, the frequency of a regular sine wave is the derivative of its time varying phase, the whole phase inside the sine, not just the phase shift. Interesting. So let's generalize that. So now instead of constraining this to be a line, we put in some arbitrary function, phi of t, whatever it is. And inside our computer, we can make such a sinusoid, at least the discrete time version of that. And so now we define the concept, not frequency, but instantaneous frequency. So really when we say speed, we should be saying instantaneous speed. What's the speed right now? Oh, then you push a little harder on the accelerator. Oh, what's the speed right now? It's changing with time. Same thing here. Same equation, but now we'll get something that's a function of time. So I put a subscript I there to drive home the idea that this is the instantaneous frequency, and we put a function of t. Nice. So if I want that instantaneous frequency to be linear, there's an equation for it. Alpha t plus omega 1. So note that starting at t equal to 0, this term would be 0. So this starts at omega 1, and then it goes up at a rate of change, frequency rate of change, until I'm done. And then it will hit whatever its highest frequency is. So that's the instantaneous frequency. I need to undo this to get back to the phi. So if derivative takes me from phi to omega, integration is going to take me from omega to phi. So I just integrate that thing and we do calc 1 kind of thing. So the phase has to change according to a very specific quadratic expression. And so if we were to make such a sinusoid, putting in this function in here, so we could compute that for a given omega 1, a given alpha over a certain range of t, then plug that in, take the sine of it. Now we've got ourselves a linearly varying frequency sinusoid, or a linearly swept or a linear sweep sinusoid. Nice. And so then we should ask, well, how do we work this out if we want to start at t equal to 0 at some frequency omega 1 and then stop at omega 2? Well, you just work it out. Turns out that your alpha needs to be that. And you can verify here that when you plug in t equal to 0, what do you get? And for the instantaneous frequency, and when you plug in capital T, what do you get? So you'd have to take the derivative of that and then plug those things in. And then here's a spectrogram of such a thing, right? So we could create this signal inside MATLAB, and then we could use our spectrogram skills that we learned a couple videos ago to actually compute this. So here's time, 1 second per division, and here's frequency in hertz. So 5 kilohertz, 10, 15, 20. So this is starting down here like maybe around 500 hertz or so, and it's going up to about 10K or so. We see that it just goes linearly here. So very nice. Spectrogram is a very nice tool to use to think about these things, and we'll use them in subsequent slides to think about what's going on. Even though we might not really use the spectrogram when we're applying this signal to test, it helps us understand what's going on from an analytical point of view. But then from a testing point of view, we could, when we're first trying things out, just explore with the spectrogram to see how things are working. Okay, so what's the inverse filter? So it's not necessarily easy to see that a linearly swept sinusoid really does have a white nature. So its spectrum is flat. It is true. It is true. And you can prove it analytically, but you can also kind of think through it, right? The sinusoid is spending equal time, so to speak, at every frequency. Its rate of change as it's sweeping through the frequencies is the same. So it's kind of like at all of those frequencies, for equal amounts of time, so to speak. So it is white, and that means that our inverse filter is just the time reversed sweep. So here we were showing starting at the bottom and going up. I suppose you could start at the up and sweep down. That would be fine too, but we usually think of starting low and sweeping high. And then if we reverse that, it's going to start high and then sweep to a lower frequency. So we wouldn't really have to build it this way. We're just using the spectrogram to think about and visualize it. We would literally just take the swept sinusoid and reverse it in time, and that's what we would get. But we can think about, if we analyze this, and again, I don't go through all the details, but if you do analyze it, we can think about this being a filter, and we can analyze this with group delays and phase delays. And what we can see is that when you do this convolution, this is basically delaying these things different amounts at different frequencies so that they all end up concentrating at the same time. So think back to when we talked about group delays and phase delays. That's the idea that we're talking about here. And so when you convolve this with this, you end up getting a delta function. What does a delta function look like? It's zero, and then everything happens at that time. And it fills all frequencies. So that makes sense, right? There it is. So we get there through a group delay view. You can actually analyze this out. I did it once in a longer version of this note set, but I abandoned it because it just was kind of long and convoluted, so to speak. But basically, we can think about the group delay delaying each frequency a different amount. And it's actually delaying it this way, right? But I find it easiest to think about it doing the opposite. So these low frequencies are moved back a smaller amount than the high frequencies are moved back. And then I have that vertical thing, which then gets delayed. All of it gets delayed to there. So that's the idea. So think about that general idea. Now, what happens with nonlinearities? We claimed that these sweeps help us when there's nonlinearities involved. So first we need to understand how to model a system with nonlinearities, whether it's the system under test or it's just part of the measurement system. But let's just look at a system. This is not one that we're measuring or measuring with, but just I've got an input and I've got an output. The simplest way to think about a nonlinear system is there's some linear system here, and there's some nonlinear thing without any either with memory or without memory. So memory just means it has dynamics like an RC or an RL system. So if you go to Farina's paper, he talks about this equation here, and he says it's memoryless, but really the equation that he writes out is with memory. This is something called a Volterra series, and it's a lot like a Taylor series. The basic idea is that this signal here, after going through this nonlinear system with memory, ends up being x of t convolved with something plus x squared convolved with something all the way out to the nth power convolved with something. And technically this would go on forever, but in reality we say, well, okay, those higher order terms can probably be negligible after some level. So if we then convolve this with the h of t here, so that little circle with an x in it is what this author used for convolution. Now we get this h1 is going to be k1 convolved with h, and this would be k2 convolved with h. But here's the bottom line. Here's the whole end-to-end thing. Still this kind of thing. Powers of the signal get convolved with something. And if it's a memoryless system, then these k's here are just basically delta functions. And so we can simplify this then. But here's the important thing. We're seeing that it involves various powers of the input signal. So let's think about this. So a sinusoid going into an LTI system gives a sinusoid out of the same frequency. But if we put it into a nonlinear system, we're going to get harmonics. We'll get the original plus harmonics. And here's how we see that. So remember that nonlinear system involves squares of it, cubes of it, fourths of it, and so forth. Let's look at trig identities, right? We're putting a sinusoid in. It's going to involve the square and so on, dot, dot, dot. But look what happens. When I square it, I get a sinusoid at double the frequency. Then I get something at triple, and I get something at quadruple. And yeah, I get some other ones in there, but that's the key idea. So we're going to get all of this harmonic content coming out if I put in a single sinusoid. So here is what happens when we sweep that sinusoid. Let me discuss it at this frequency. So at that frequency, here's my original signal going in. There's my linear sweep, right? I'm going to get the original signal out. So my output of some nonlinear system, I put a linear sweep in, I'm going to get the original linear sweep out. But I'm also, at every instant of time, I'm going to get double, triple, quadruple, etc. So what do I have? Here's a frequency. Here's double it, triple it, quadruple it, etc. So you see, you get these diagonal lines like this. Those will all be there, and they'll have different varying amplitudes. And the reason they go kind of in and out here is just because we're numerically computing these things with a sliding window and so forth. But this is the idea. So those are the effects of the harmonics that come from the nonlinear part of the system, either the device under test or the measurement system or both. But here's the main thing. That's going to have information about the original linear part of the system. So when the inverse filter is applied, remember we talked about this idea originally with no nonlinearities, and we said that the linearly swept sinusoid, due to the group delay effect of this filter, right? We're convolving, so we think of this time reversed signal as a filter. It's going to have a group delay that's going to delay all these. And like I said, it's easiest for me to think about everything being kind of moved backwards and then moved forward, the amount necessary to put it where it is. But, I mean, you could think about this being moved forward and this being moved forward, but it's easier for me to think about it being moved back. It just works out in my mind better. So this thing's going to move back and create this vertical thing, which ends up here. That's the impulse response, the spectrum of the impulse response of the linear swept signal. But then all these other ones here, they'll get moved back the same amount. So that one there ends up being tilted backwards that amount. And the next one up gets tilted back even farther because they're all being subjected to the same amounts of delay. So what does that do? That means that this creates the delta function of that convolution that we need, that autocorrelation that gives us the delta function. And what is left? All of this stuff, but it's out of the way, right? It's back here. So I can extract stuff from here. This would be, you see all that fuzzy stuff going forward? That's the impulse response nature of the linear part of this system. So this is beautiful. If we think about converting this back into the time domain, but remember, this is not how we do it. I'm just visualizing it this way. We literally just take the output of the system after we've put the linear sweep in and convolve it with the time reversed in the time domain. This is all done in the time domain. And then we get this. And so this part here is coming from this part. That's just the linear part of the system. And so that's our impulse response. And then all of this stuff is all down here, but it's all mixed together, right? So the nonlinear part is just pushed out of the way, has no effect. But we can't really tell what all those different linear parts are doing because they're all on top of each other. But we can identify just the linear part. So remember, this is delayed, so we'd have to account for the amount of the delay. You can work that out if you're working through this. And then we would just keep from that point onward, just this part. That's going to be the impulse response of the linear part. So if these nonlinearities are coming from the measuring system, beautiful. The effects of the nonlinear measuring system are out of the way. That's nice. Now, that was good. Why would we want to do anything else? Well, let's take a look at what happens with the exponential sweeps. And this was all first developed by Farina. This was a huge insight on his part. So he deduced by looking at this and analyzing it and thinking about it from the spectrogram point of view, he worked out in his mind and on paper probably that the exponential sweeps should work even better. So let's think about an exponentially changing frequency. So here's the general structure. You'll see why we define those parameters like that. But basically, it's a constant out in front and then a coefficient in front of the t, 1 over L. But just written out in terms that will make physical sense in just a little bit. So that's the frequency that we want, changes exponentially, sweeps upward exponentially. And so we want to get the time varying phase function. So we're just going to integrate that just like we did before to get the the linear sweep, we started with a linear frequency and we integrated it and got a quadratic phase. Well, now we integrate this and well, integration of a exponential gives us some kind of exponentially related thing. So there's what our phase needs to be. So we literally choose the K and the L. We'll we see right here how we pick those. So we say, oh, I want to start at omega 1. I want to stop at omega 2 at capital T. So you plug all those things in here and you get your L and your K value. Now you put that K here and you put that L here. Generate this phase, put it inside a sine, and now you've got your exponentially swept sinusoid. Nice. And it turns out it's not white, but it also is not zero at any given frequency. And the reason that it's not white is we can kind of think about, because the rate at which it sweeps through frequencies is going faster and faster as time goes on, it kind of spends unequal amounts of time, quote unquote, at each frequency. So the spectrum's not white. And we can actually analyze this. I just did a quick FFT analysis of this, but you can analyze it analytically and you can find out how it drops off and things like that. And you can find out that it drops 3 dB every octave. And Farina makes an argument that that's better for room noise, because HVAC systems tend to have be louder at low frequencies than at high frequencies. So he argued that that was yet another advantage to this. So we need our general inverse filter, and we could just think about, at least theoretically, reciprocating this and taking the inverse and so forth. This is what the spectrogram of that's going to look like. But notice it looks linear. That's because I've got my frequency axis on a logarithmic frequency scale. So this exponentially swept sinusoid will have a line on this spectrogram when the frequency axis is logarithmic. So our exponential sweep inverse filter, we said that the probing signal, its spectrum goes down 3 dB every octave, so we need to have this go up 3 dB every octave, and we need it to have a negative phase. So that means our group delay will be reversed from what we had before. So if we use all these ideas, basically we end up being able to make this thing go up. Because of both of these issues, we'll need the reverse sweep to go up 6 dB every time T hits a point where omega sub I goes up an octave. So our amplitude is going to have to change on the sinusoid. So for the probing signal, the amplitude is constant, but for the inverse filter, the amplitude is going to go according to this. So the amplitude of the reverse sweep will follow that formula. And so now let's just look to see what we got. So, I didn't go into a lot of details about how we got that inverse filter, but you can check and verify that it does indeed do what it does. Now, these three spectrograms are all with log frequency axes, so keep that in mind. So here is this is after it's gone through a system with nonlinearities. And if we do the same idea with the harmonics, but because we're on a logarithmic frequency axis, we'll see that we get these kind of parallel lines rather than what we had before with those diagonal lines, all anchored at one place. So this is because of the harmonic, or of the exponentially swept nature that we get these things. You'd see a totally different structure if you did the linearly swept sinusoid, even on the logarithmic scale. So remember, this is our inverse filter, and it's going to cause group delays that will make this thing end up vertical. And then it moves forward by some amount. The whole thing moves forward. So that gives us this thing right here, which back in the time domain, I don't have these lined up, but back in the time domain, that gives us that. So that's the impulse response of the linear part of the system. But here's where the magic happens. This line, that's due to the double frequency components, due to the nonlinearities. It will also, because it's parallel to this, right? This and this are parallel. They're both being subjected to the same group delays from that. It will end up vertical as well, with some tails, right? And so that creates this. And then the next one up creates this one. They all end up vertical with some tails. And as long as those tails decline or decay before you hit the next one, they don't overlap. And so what does that tell us? These are all of the impulse responses that we can use in a Volterra-based implementation if we wanted to analyze or simulate that system. So we don't need this when we're just trying to find the linear part of a room and all we care about is getting the nonlinearities of the measurement system out of the way. But we do need this if we want to try to mimic a nonlinear audio system, not a audiophile system, but guitar amps and things like that, compressors, things that we'll study that are inherently nonlinear. We need to know all this to try to mimic those. And so this exponentially swept sinusoid idea gives us the ticket. And we'll see later. We won't go into all the details, but we'll see later where we might be able to take advantage of this to simulate or emulate, I guess is even a better word, emulate some sort of nonlinear audio processing device. So that's the idea. So all the individual harmonic impulse responses are all separately available here. And if you want to model your system, a nonlinear system, you can extract these things and use that.